All right, aloha. I'm going to talk to you today about Android's boot firmware, specifically recovery mode, and hopefully learn some things. So nice to meet you. I'm Drew. I'm a security consultant for NCC Group, formerly Matasano Security. I focus mainly in mobile security and research. I've built Android firmware for dozens of devices, probably 50 plus at this point. Part of the open source side of the CyanogenMod project, I built and maintained the wiki that teaches you how to exploit your phone and put CM on it if you'd like, or any other operating system. And my cool guy internet handle is utkanos, if you want to follow along on GitHub or anything like that. So what is this all about? Big questions is, why do I need this? What's interesting about this for security? So we're going to talk about that. We're going to talk about what bootable recovery is. We're going to talk about how to do what we call device mapping, which means you have a device you already own, or maybe a brand new device that nobody's worked on, and you want to sort of case it, like figure out how the internals work. We're also going to do some firmware inspection, looking at some bootable firmware, figure out how it works, and then we're going to talk about how you can flash what you've just learned how to build on your own. So what is Android recovery? The stock recovery is on pretty much every shipping Android device, and you kind of have to do what we call like the grip of death to access it. There's usually a button combination that will boot you into this specific mode. Lots of devices have multiple boot modes. Typically, recovery is bound to one of those. And it's essentially a very minimalistic like Linux environment that boots up the kernel, typically the same kernel as like what boots the ROM. And it's very basic. The stock recovery will basically let you do like a factory reset if you've screwed something up terribly with an Android, which will clear out the user data partition and the cache partition. And it's also used to install signed over-the-air updates from your carrier or from your OEM. So whenever you get like a new version of Android, it boots to recovery to install that and then boots back up. Sometimes you'll get ADB access, which is the Android debug bridge, but usually not. And even if you do, it's pretty useless because the stock recovery is very limited in what it lets you do. So custom recoveries provide root access, most importantly, but they also can contain any useful binary that you want. So if you need a specific tool and you want to be able to work with Android in a state where it's not booted, but you still need to impact the file systems that run it, that's a great place to do that. It also allows for easy backup of essential firmware. So if you're messing around with your phone, it's really good to have like a standard backup of all the images that you're messing with, just in case you break something and need to restore it back. And it provides sort of like the scriptable installation platform for custom Android. There's a scripting language called Edify, and using that you can do all sorts of interesting things like change permissions on files, install things to specific places, and you can automate that. So it's really useful for that kind of thing. So why is this significant? I think this question will be answered the longer the talk goes on, and the impact will be more significant. But right off the bat, they provide a means to investigate and modify and test new firmware. So it's a great sort of little bootstrap platform. And in many cases, it gives you full control over a device. So what is this for? Why do I need this specifically? This is great for like penetration testing. It's great to have like a snapshot of the platform you're working on before you start making changes, so you can roll back if you need to. It's great for forensics and data acquisition. There'll be more slides on that towards the end. It's also a means to bypass security controls. So if somebody leaves their phone in a Starbucks or whatever, and they have a lock screen, and they've elected not to encrypt their user data partition, you can simply just boot and delete that in a lot of cases. So bypassing those kind of controls. And it's also really useful for testing and development of custom Android installations as well. So how do I make one of these things? So what we need to do is map out the device topology in full. We need to get the kernel source for it or the pre-built kernel, just so you have sort of like a working known image. And then we need to build what's called like an Android device configuration, and I'll show you that upcoming here. So bootable recovery. I got into this basically because I realized like I was sort of a Unix admin for many, many years before getting into security, and this was basically a little Linux box, so I kind of already knew how that sort of stuff worked, and it helped me get into it a lot more. Thanks for the one laugh at my shitty Jurassic Park reference. So every device is kind of a unique snowflake, as we like to say. So the sort of the canonical example of this is Samsung sold a phone called the Galaxy S2, and I think there's like 15 variants of that phone. So the sales name of device is entirely useless in determining like what's actually in it, because they resell very vastly different hardware and configurations under the same name in a lot of cases. And this is sort of changing for the better. It's becoming more modern. But you can never really trust, like if someone says, hey, I have a Galaxy S2, you need to ask more questions about it, because the partition layout is probably different and you will probably brick it if you have the wrong one. So it's interesting to see like the variations that are out there. So the parts and structure of a recovery image. I'm going to talk about like the two most popular that you'll see in the wild. There are a lot of variants out there of this, some very interesting variants, but the most typical is just an initial ramdisk image, like what we call like a standard boot image. It has like an Android boot header. It's got the kernel itself, and then you have like an initial ramdisk as part of that image. Samsung for many years used this next style called an init ramfs style, which basically means that the ramdisk is compiled into the kernel, and you just flash the Z image itself. There's no other part of the image. This is obviously like not great, because the whole point of recovery is that you can modify things and have a working kernel when you're done. If you flash trying to get a custom recovery and you fail, you've lost your ability to boot the ROM as well. So like this was originally done to save space on flash memory, where they could just share one partition for this, but like this has largely changed, and Samsung has stopped doing this. But you still run into this on many, many devices out there from that era. And then there's like kind of this third variant here that Sony still uses called like, it's the same idea as the init ramfs, where it's shared one partition, but it's actually just a normal boot image like you would see on most phones. And again, basically just sharing one partition to save space here. So here's kind of a look at how these very typical images are built. You've got your boot header, your kernel, your RAM disk, and then I've sort of called out, sorry if it's a little hard to read there, like slots 10 and 11 are used for DTBs, which is like device tree blob, device tree binary, depending on who you ask. But these are becoming more and more popular on images, such that they don't have to write an entirely new kernel. They can just attach the interesting bits that are different in a DTB file on top of the image. So for example, the Galaxy Note 3 was available in many markets, but had sort of just different DTB files instead of like a whole brand new kernel image. And stuff like NFC and Wi-Fi differ between even these variants, and like those things are kind of captured in there. So the initial ramdisk works very identically as to like a Linux box. It loads a temporary root file system into memory. It only has very minimal files specifically used for the recovery mode operation. There's a whole host of init scripts in here and a packaged init binary that comes as part of that. And this can be rebuilt or modified. Typically recommend building this from source, but a lot of times you don't have kernel source, or you're in a situation where you have the init ramfs style where you can't just modify it. You have to actually rebuild it. So it is possible in some very like weird edge cases to modify an existing image, but almost always it's too hacky to deal with, and you should just build it from source. So also in the recovery is a file, everything including and less than Android 4.2.2 Jelly Bean had a file called recovery.fstab, and this is identical to the etc fstab that you would see on a Linux box. It just sort of maps the block devices and the file system types to a specific mount point. And this usually lives in the etc folder within the RAM disk, or sometimes res on older HTC and Samsung gear. The newer style is fstab.platform, so examples of fstab.qcom or fstab.msm8974 for that particular Snapdragon processor. And you see this after Android 4.3, this is sort of like the newer style that they've moved to. pretty much works identically, but there's a slightly different mapping order, so that's just something to keep in mind depending on if you're building one of these. So it's time to begin sort of casing this device so that we can build our own recoveries. So what's the bare minimum we need to get this thing off the ground? The stock firmware is extremely helpful for this because it has like the exact image that your phone is booting already. You know that the Z image in there is good and it's going to boot your device. So it helps to start with like minimal variables. So you have this working firmware. And it's also great to just kind of pull this apart and figure out how it works, which I'll show you here coming up. So there's actually a lot of sites that host this kind of stuff. Or if you have a rooted device, you can just use DD to dump the partition you're interested in. And it's really useful for like troubleshooting weird OEM hacks that people have done to make things work. And I'll kind of get into that more, but more so just to build yourself a device topology here. And of course, the kernel source I just mentioned, you basically have to have this for init ramfs style images. It's also really useful for making a kernel smaller. So for example, like many older devices only gave you like 5 megabytes for recovery. So if you're trying to build something fully featured and add a lot of interesting binaries for whatever you need it to do, you're not going to have a lot of space on these older devices. So if you have the kernel source, you can whack out a bunch of stuff you don't need for recovery to make that outputted Z image smaller so that you can fit more of your own tools in the RAM disk. And these can obviously be modified for anything you need to do, so that's also helpful. We'll talk about a file called build.prop. So this is in the system of Android, and this contains sort of parameters and all the various different options you can pass. So there's a lot of stuff in here, but what specifically we're most interested in is the device-specific board codename. And so this kind of goes back to the Galaxy S2 example I mentioned, where that means nothing to us. We need to know like the board name itself. So that's a parameter called out in this build.prop file. And that's how we identify and name a device, is by the board codename. If they were nice and left you a proc eMMC or a proc MTD, you can get the partition mapping directly from that, and that will give you the block device and like what it does. So that's really helpful for when you're trying to build one of these, or just figure out where things are on the device. And then the proc partitions output will give you the block sizes, so you can sort of compute how big each of those partitions is supposed to be. And this is also really useful for making sure your recovery fits in the space allocated. And then, if you can't find the kernel source, you can at least get the def config off the device a lot of times. I've seen them strip this out more and more recently, but you can usually get it in the kernel source drop. And OEMs have become much better about that. Like a couple years ago, it was really hard to get them to post kernel source on time, or it would be like 6 months later, stuff like that. So, all right, so let's look at how to take apart some of these firmware images here. So here we have a look at the standard Android boot image. You can see that called out there in orange is this Android bang. This basically tells us this is a bootable Android firmware image. Afterwards, you see if there's a kernel command line, it's passed in as well, and I've also highlighted that in orange. This is something that you should definitely replicate when you're building your own image, because it probably won't work if you don't pass these specific values at time. But if you're starting to look at some of these images, you can use something like octldump to make sure, like, okay, yeah, we can clearly see this is an Android boot image. So talk about a couple tools. The first one, unpack boot image. This is an older tool that's largely been surpassed by by this other tool, but still kind of give you this usage here. So you basically take in a firmware image and output to wherever, and then you use Zcat to pump the RAM disk to CPIO to explode it out. And this will give you sort of like the actual files that are contained in that RAM disk. The newer tool that supports much more in the way of different boot firmware image types is called MakeBoot. And I've sort of keyed these so you can look in the references to get source code for these files. But this is essentially a very similar idea. It just takes the boot image, breaks it apart, and gives you like the stuff that you're interested in. There's also the unpack init ramfs shell script that somebody wrote out there to extract this out of an older style Samsung phone, but we'll kind of talk less about that. And then there's always good old binwalk. If all these tools are failing, you can sort of locate, okay, this looks like a RAM disk. I'll use DD to snag this out and then look at the files that way. So I've had to do that on a few devices that just have very random, non-standard setups. So here's kind of a look at how MakeBoot works. I've highlighted the interesting parameters again in orange. So you always really wanted to record the kernel page size because you have to make your image follow this format. Most of them are 2048. HTC specifically uses 4096, and then you have weird one-offs like Rockchip, which are like 16384, or just some like horrendous size like that. But you definitely want to match that in your image or it won't boot at all. And then the other really important thing here is the ramdisk offset. Because if it cannot find this ramdisk at boot time, you'll get like a nice black screen and you'll have a sad face that you've broken your ability to boot your phone. So you definitely want to match that offset so that your ramdisk loads at that address. And then the DTB image I mentioned earlier, it will also extract that blob for you so that you can reattach it when you build your own image. And then, of course, the command line I just mentioned that we saw in the dump there is also called out here. So our goal is really to get the ramdisk and a working pre-built image. Like, that's the place to start if you want to start building this stuff. The ramdisk, as I mentioned, contains really important init scripts, custom scripts, and binaries we want in order to make our device work. And as you'll see coming up, the init scripts are very useful for finding exploits in devices because they're not written very well in a lot of cases. So why are these init scripts so important? They're a great source for bugs. There's so many out there, especially like in the last few years, that have these sort of classic Unix attacks like symlink attacks coming back and still being sort of very active there. Very overly permissive permissions. You'll see stuff that's just chmod to 777 or some other world writable setup there. And you also see a lot of debug functionality exposed. We've seen like just sockets that have been opened that can be nothing else but like a backdoor, basically. So like these init scripts are really interesting to look through and look for flaws. But they're also really useful in helping you build your own tools because sometimes you need to emulate what they're doing in their init scripts before you can move on. There's also things like watchdog daemons that you'll see in the ramdisk, and I'll kind of talk more about those coming up. But you get a lot of parameters and basic information from these files. So let's look at a couple examples here. These are reprinted with kind permission from my friend JCase. And these have all been patched, so I feel comfortable sharing these with you. But here's a kind of an example of where these things can fall down for you. So there's a directory that's created with 777 permissions. And there's also a file called mid.txt created the same way. So knowing that we have these files in the data file system, we can push our root exploit to data local writes because we have full write access to that directory because of this error in permissioning. We can rename the existing file again because it's world writable. We have the permission to change that file in the data file system. Then we can do something like symlink the uEvent helper to mid.txt. And essentially, this is a kernel helper that will execute anything in the context of root. And this has sort of been patched to not do that anymore, but this is alive and well in lots and lots of devices out there. And so now we just sort of basically echo our root exploit into uEvent helper, and it executes in the context of root, and now we have a persistent root because of this. So now you have a cool shell. Another example from HTC here. Again, we have an overly permissive directory. This is also created with 777. And then we have a log file in here, which is 666 world writable and executable. So what can we do with this? Again, we can remove the existing file because it's world writable. We can symlink data local.prop to this log file. And when I mentioned the build.prop earlier, this is how Android reads in all these parameters. It will also respect a local data version, so you can override what's in the system with a file like this. So now we can reboot to recovery where these files are actually executed. And there's a string here that tells ADB that we are running in an emulator so that ADB should restart as root. So we can echo the RO kernel QEMU1 to this file, do a reboot, and ADB will temporarily reboot with root capabilities. So this gives you kind of like a one-off shell, but you can use that shell to make a more persistent root if you'd like. So what else is interesting in these files? I sort of mentioned watchdog daemons. This is something that needs to bark every X interval of seconds. So I've seen it 30 seconds. I've seen it all the way up to 10 minutes. if it doesn't check in at that time, it will just rip the carpet out from you and reboot. So like this is not a great thing to have happen to you if you're doing some work on your device and it just shuts off in the middle of that. It can lead to bad things. So these are things that you have to replicate in your images. There's also sometimes like necessary kernel objects. So I like to pick on Rockchip a little bit because they're crazy, but they do things like wedge ext4 on top of like an MTD flash device, and they wrote their own like flash translation layer to do this. This requires their custom kernel objects to be loaded, or you just have no storage whatsoever. So this gets a little hairy in terms of like making that stuff work, but you see some horrible things out there. There's also sometimes some special commands that you might run across in these files, like not always, but it's interesting to take a look at them anyway. So what happens if I can't figure something out? If you're lacking firmware and you really don't have a lot to go on, you can do a little manual investigation using ADB shell, even with like the limited privileges that will give you. You can look at mount and at least identify like 3 of the key partitions of this thing, so you can get system, user data, and cache typically. And then you can really just look at the sizes and proc partitions and make an educated guess for firmware locations. So if you see something that's in like the 5 to 20 megabyte range, that's a good candidate for a boot image. They're not going to give it more space than that, and they can't give it less at this point. So you can kind of make educated guesses on like, okay, this is probably what I'm looking for, and then you can dump that and investigate it further. So we'll talk now about how to build one of these things. Android's build system is based on like a meal ordering concept. So it's sort of like when you roll up to McDonald's and you have like the 1 through 12 combo options. Each device is a unique combo meal that we need to load into our build environment. And you should also note that combos can also inherit from one another. So if you have like a common core that like 10 devices share, you might need to also replicate that if someone's already done this work for you. So look at the inheritance of these make files and make sure that you have everything you need. And essentially what we're trying to do is build a new combo. We're going to put your favorite sandwich on the menu so that you can start ordering it. So how do we build one of these? You can use the CyanogenMod source or any Android source out there. I've linked some examples here. You need Linux or OS X to do this. I've seen people attempt this in Windows, but I don't hate myself enough to try that. And we basically need all of the info that we've gathered in these previous sections here. So there's a handy little script called make vendor that will generate a very skeleton sort of bare bones config for you to start working with. It takes 3 parameters, as you can see. It's usually the OEM name, the board name that we found out earlier, and then a bootable image of any kind. So it can be the recovery, it can be the kernel, boot image, whatever you want to use for that. In this particular case, this is the T-Mobile edition of the Galaxy Note 3. So unfortunately, make vendor output is always wrong and pretty incomplete. So it gives you the files you need to get going, but it almost always needs like custom attention paid to it. So don't take what it generates for you at face value because it's not going to build. But I'll talk about the 3 most important files that get generated here, which are the board config, the FS tab I mentioned earlier, and then there's a device codename make file that gets generated. And so here we can see this is the Droid DNA, I believe, on Verizon. And I've sort of marked with an X the files that make vendor generates for you. Everything else in there is something that I added as part of trying to get this recovery to kind of boot up on it. But that kind of gives you a good example of like, here's what's generated, and now go fix it, basically. So we'll talk about the board config itself. This contains the essential information about your device's board, the CPU itself, various hardware contained like Wi-Fi and Bluetooth and stuff like that, and other device-specific oddities. So if there's like sort of, you see a lot of these hacks that vendors have put out there that you kind of have to replicate in your board configs to make things work properly. This requires absolutely like the most modification, and this file continually grows the more you build out. So if your goal is just to build a recovery, like it's pretty minimal, but if you want to get Android built completely from source, this is going to continually evolve and have more and more stuff added to it as time goes on. And sort of for the scope of this talk, I'm only going to talk about the basics for recovery, but there's plenty more out there that you need. So particular interest to us are making sure that this ramdisk offset is set properly. I sort of mentioned that earlier when we were talking about the make boot output, but the first parameter is largely deprecated these days, but if you're working on an older device, this is the parameter that you need to set, and this is the address called out by make boot that you have to set properly. The more modern version of this is called make boot args, and this is really important on larger partitions where you're putting something smaller back. So if you're building your recovery, it's not going to take the full extent of that partition. The ramdisk is going to be totally offset improperly unless you force it with the make file here. And again, as I mentioned, that first parameter is largely dead after 4.1, but you still sometimes see it if you're building for older phones. So the device-specific make file here lets you basically take images in the ramdisk and put them where they need to be in your compiled output. So if you want to put your own tools in here, something that's not standard, or that's something you want to add to your image, this parameter, or this file will allow you to map where this is in the combo and like where it needs to be when the image is built. And so this is sort of essential for like emulating these OEM-specific oddities, like I mentioned, or like a watchdog daemon, for example. Like you need to copy that into the ramdisk at compile time or it won't work. So this is the way to do that. And then we want to build it. So using lunch to go with this whole combo ordering scheme they decided on. We sort of load in the build environment. We run lunch on the device that you just created, and then you can run make recovery image. There's lots of other make targets out there, but for the purposes of this talk, this is the most common one. Feel free to browse that make file and look at all the other stuff you can do with this. So then we want to test it. I mean, I think a lot of like really dumb mistakes can be caught just by investigating the firmware you just built, similarly to how you looked at the stock image. So if your ramdisk is offset improperly, for example, there's no reason to flash that to your device and potentially brick it. You can easily catch that error before you do it. So make sure you kind of look at these things, compare it to stock, and then also make sure it fits. Like if you've built something that's too big for that partition and you try and flash it, you're going to have a bad time. So make sure that the size is working there. So common issues, this is really what it feels like to work on one of these sometimes. You just mash the keyboard until it works, but you're probably not gonna get a boot on your first try. I think more realistically, you won't. And here's some common reasons why. I won't really get too much into these because there's other stuff to talk about, but you know, stuff like the offset's wrong, the kernel page size is wrong, and it's misconfigured. There's some weird OEM hack you're not emulating, or you forgot to attach a DTB file, or it's wrong. It's for the wrong device, so it just won't boot properly. All right, so now we'll flash it. Here's the interesting part. So how do we get this onto a phone? Because I'm sure a lot of you are thinking, well, there's a lot of protections that prevent you from writing these kind of firmwares out, and how do we do that? So there's good old DD, sort of obviously requires root, but you can kind of refer back to the init portion of this talk for some ideas on how you might be able to obtain that on your device. The flash image binary is pretty well deprecated now because most devices don't ship with MTD flash anymore, but this will basically just take in the parameter of the image and the partition you want to flash it to and do that for you. And then these last three are the interesting ones that we'll talk about. There's the Samsung-specific download mode. There's fastboot, which I'm sure a lot of you might be familiar with, and there's sort of this newcomer laugh, which is named properly because it's hilarious. And this is for most modern LG devices at this point are vulnerable to this silly little mode here. So let's talk about download mode first. This is a Samsung-specific boot mode. How many of you guys have Samsung phones? How many of you encrypt user data? Okay, maybe you would like to after seeing this. So as I mentioned, download mode is a Samsung-specific bootloader interface. It's shipped on all of their devices. It requires specific naming of images, which can be a little tedious, but it's not really that bad. And internally, Samsung uses a tool called ODIN to interact with this. Unfortunately, this is a Windows-only closed source application that's leaked from Samsung internally. And assuming you don't have something on Verizon or AT&T, which actually does enforce boot image signing, all their international phones and phones on other carriers have this mode. And this is essentially like a super permissive bootloader mode. So let's take a look at ODIN. This is a terrible piece of software, but sometimes you need it. Sometimes the device just won't work without this. We'll talk about the alternative coming up here. But this essentially takes in the file you want to flash and just pushes it right to the bootloader for you. So ODIN, interestingly, requires a U-star formatted tar archive containing the desired firmware, which is kind of amusing because there's no real native way to do this. And in Windows, which is what ODIN runs in, so like you kind of have to do this with like a third-party tool or on a Linux box or something like that and then transfer it over. But here's how to make one. So you can essentially put whatever file you want in here. You just create the U-star formatted tar archive. ODIN gets really cranky if there's not an MD5 sum attached sometimes. Sometimes it doesn't matter, but it doesn't hurt to do this as like a step because it'll work either way. So generate the sum and attach it at the end of the tar, and then rename it to tar.md5, and now you have a file that's ready to go. So the naming, again, as I mentioned, is very important here. So recovery.image has to be called that. It can't be called anything else. If you want to do a boot.image, similarly, that has to be called boot.image. You can't name it anything else, or ODIN will just flip out and say, no, I'm not going to do this for you. So the alternative to ODIN is called Heimdall. This is made by this Australian guy. And this is great because it's cross-platform. It was created basically by reversing what ODIN does, and this will work on any operating system. It also doesn't have silly restrictions on naming, and it's capable of flashing raw images directly, so you don't need like a U-star tar file. You can just write the image you're interested in. And obviously that makes this much more flexible and useful than ODIN. So we can see kind of the obvious problems here. This is extremely overly permissive. Most devices allow like a direct write access to the partition in question here. There's a handful of US models that are protected against this, as I mentioned. But that's definitely like the outlier. Like the majority of these, you can write directly to the device. And there are newer protections for this that protect against it, but they're extremely inconsistently applied. So for the most part, if you have one of these devices, it's something to think about here. So let's talk about fastboot mode a little bit. Fastboot is probably the most common interface you'll see. It's found on all the Nexus devices, HTC, Sony, Motorola is using this now, many other OEMs. Fastboot is great in that you can actually test an image before you flash it to the device. So if you just run fastboot boot and the name of the image, it'll download it from your PC into memory and boot it, and then you don't waste a flash cycle, but you also, more importantly, don't overwrite it with something that doesn't work. So that's a good way to test things. Unfortunately, unlocking the bootloader to use fastboot most often erases the user data partition, which is a lot of times what we're interested in. That is unless you have many published CVEs in the bootloader you're using. So Little Kernel from Qualcomm has had a lot of problems in the past that would allow you to bypass this lock or various other things. So the first one, they just forgot to check if the image was signed. So like that was an interesting one. The next one's a little bit more tedious to pull off. It uses the kubroot attack. Sort of like you should follow that up. It's a little complicated to execute, but you can forge a signature on your image and get it to boot something that's not signed. And the last one is relatively new. They didn't check the bounds for sparse images, so when they flash system as part of an image, they don't actually check like where that's supposed to end, so you can write past that barrier and impact other partitions on the device. So we've talked about download mode and fastboot, so let's look at LAF. This is a relatively new thing. There's a bootable partition named LAF, not LA, sorry, found on many LG devices. What surprised me the most was this is also on the Nexus 5. There's communication that's possible when you boot to this mode with a binary called send command. And send command takes one parameter, which is the COM port that your device is plugged into, and it basically drops you to a root shell on the device. So this is pretty clearly a backdoor. I think they probably use it for diagnostics or flashing firmware, but like if you just leave a root shell out there, that's not a great idea. So here's like an image of that in action on the Nexus 5. Again, sorry, that's hard to read, but you basically just run send command, pass the port, and now you can see we have a root shell on this device. So lastly, I'm going to talk a little bit about forensics, kind of circling back to what we were talking about earlier. There's a group of German guys came up with this tool called Frost, which is the forensic recovery of scrambled telephones. This is based on a custom recovery that is very popular, based on the Clockwork mod recovery. But this can be used to retrieve encryption keys, PIN codes, stuff stored in RAM. And it actually uses like quite literally a cold boot attack. They figured out that if you put a phone in a freezer, it slows down the degradation of RAM enough that you can actually quickly boot into this mode and snag things out of what was left in RAM. This uses the AES key find binary. You can do this live, or you can also just dump the contents of RAM to your PC and run it there. And this just looks for like AES key signatures and sizes and stuff like that. There's also work being done with like the volatility framework and Lime, which is like the Linux memory. I forget what the E stands for, but basically you can view the contents of RAM. So this is another interesting way to potentially recover somebody's like pattern or pin lock code. So what's being done about this sort of stuff? New protections. So we now have init context that you're kind of seeing rolling out. So things that are executed at init time don't necessarily run as root anymore. They're sort of segregated into like other service levels. So you're not going to be able to execute a lot of these like interesting attacks anymore because of that. There's things like Knox and Secure Boot, which is coming out on more and more models. Unfortunately, this is largely useless at this time, except for the models I mentioned that are protecting or are verifying these boot signatures. But at worst, you'll get like a nag screen saying, hey, your boot's been tampered with. And you'll see it for maybe 2 seconds as the phone reboots. So like it's not something that's going to really stick out in somebody's mind if this has been done to their device. Now they're sort of wrapping the device encryption key with an ID from TrustZone or like in a trusted execution environment. So this prevents you from attacking like off the device essentially. Like you need to do it on the phone now if you're trying to brute force things because you need that ID. They're increased SE Linux presence. They're doing things like blocking your view into like /dev now, which is totally pointless. It's going to slow you down a little bit, but not much. Protections like DM Verity. This is really not rolled out in production yet, and it's probably something that's coming. But this does like basically like a SHA-256 of every block of the system partition, and if any of those blocks have changed, it will just refuse to boot. So this kind of kills your ability to modify system for a persistent root. However, if you have the ability to overwrite boot images like we just talked about, you could just flash one without DM Verity enabled and then game over. So there's also Force Encrypt, which is the sad face because this was supposed to roll out with Lollipop, and then Google kind of changed their mind and said, well, no, it's still optional. So none of the OEMs really did it. I think like the Nexus 6 and the Nexus 9 shipped with this, but pretty much everything else just still had it optional. So that's something the user would have to enable themselves, which is not as likely unless you're security conscious. So getting started. GitHub is definitely your friend. It's more than likely that someone's already done this work for you for a particular device. So you can find these device configs out there on GitHub. And again, I mentioned many sites host like stock Android firmware images. So if you're looking for Samsung specific things, samfirmware.com is a good place for that. Of course, the XDA forums people always post like stock images and stuff like that out there. So setting up your build environment, I put like a pretty good guide out there on the CM wiki that talks you through like all the packages you need to get started with this. You don't have to use CM source. You can use whatever you want, but that's a good guide for, I'm using a Linux box. Here's the tools I need to do a successful compile. Definitely review the links in my references section. Some links to source code and more information about some of these CVEs we talked about. And then also just wanted to mention the DroidSec community. If you guys are interested in Android security, this is a pretty good group of guys. And there's like an IRC channel and a site. So if there's always really interesting talk on like new exploits that are coming out or what people are working on. It's good to follow up there. So here's the references section. You guys can take a look at that later, rather. So that's all I have. Just wanted to thank ShakaCon, not that ShakaCon, for hosting, and it's been a wonderful experience. So if any questions, please let me know, or find me afterwards anytime during the con, and we can chat about whatever you'd like. Any questions? Yeah, and then the back. Not really. I think, like you said, the USB cable. I have built, so like to force a phone, like for example, like a lot of Samsung phones, you can force into download mode if you can't actually get it to boot that way by shorting like 650 kilo ohms across the ground and ID pin. So I have like a little breadboard and just cut up a USB cable, and then it just boots the phone immediately into download mode. But that's pretty much a USB cable and a little bit of extra tools. So otherwise, no, that's the main communication method. All right, cool. Thank you, guys.
Thanks, man. Sorry for going a little long.
Oh, no, that's okay. Check. Mike? So who here thinks that you